Okay, welcome back to Mr. Burley Teaches, a series of lectures for the AP Environmental Science classroom. Today's lecture is ozone. Okay, now that we know a little bit about the structure and composition of the atmosphere, we can dive down and take a deeper look at three important variable gases, the first one being ozone. Ozone is important for life on Earth. Okay, if we did not have ozone as a variable gas, concentrated in the stratosphere, Earth would be a very different place when it comes to life on Earth. It's something that we want to understand. We want to make sure that we pay attention, all right, to levels of ozone and what we're doing and how our human actions can affect something that's way up there in the stratosphere, so far away from our lives, so invisible, so unknown, so out of sight, out of mind, but so very important. Okay, so let's take a look at ozone, the O3 molecule. Ozone forms naturally in the stratosphere. Okay, very easy process to understand. It takes oxygen and UV radiation to build an ozone molecule. So, it's very natural to have O2 in the atmosphere, but UV radiation, high energy radiation, can and does break apart that bond between an oxygen and oxygen. So now you have a free-floating oxygen molecule, all right, which then collides with a different O2 molecule to form a bond, and there you go. You've just made an O3 molecule. All right, so very natural process. All it takes is UV radiation, which the sun supplies for us, and free oxygens combine with O2 molecule. So what you need to take away is that it forms naturally, and it will rebuild itself. Now that you know a little bit about ozone formation, let's take a look at how ozone was being destroyed. Our human actions that were depleting the ozone layer up in the stratosphere. So, I have a little city at the bottom that represents civilization. And what we were doing, we were adding a chemical to the atmosphere called a CFC, chlorofluorocarbon. Okay, CFC. And that molecule looked a little bit like this. Right, so there's a carbon, 4 bonds on the carbon molecule. There's 3 chlorines and 1 fluorine. Okay, so that's what a CFC looks like. A little bit something like that. 3 chlorines bonded with a carbon and a fluorine bonded with a carbon. All right, and that chemical was readily used in things like aerosols. Aerosols are spray cans, spray paints, hairsprays, anything inside of a can that used a propellant to eject the material inside the can. Aerosols and refrigerants and coolants. So the manufacture and use of refrigerants and coolants throughout the 1950s, 60s, and 70s were adding CFCs into the atmosphere, which got up into the stratosphere and began to break up ozone. CFCs were first discovered in the late 1920s, all right, and then were used extensively throughout the 50s, 60s, and 70s. So, as you're going to see in a little bit, it takes a while for that molecule to get up there, do its damage, and then leave the stratosphere. So, even though we banned CFCs in the late 1970s, the ozone hole was deteriorating all the way through the early 2000s. All right, and here's how it happened. So the sun gives off natural UV radiation, which if a CFC is high in the stratosphere, it's exposed to UV radiation, and the UV radiation will break the bond between the chlorine and the carbon. And now what you have is a free chlorine. All right, and you can follow along looking at the formula down here. I'm going to go through this formula down here in the lower right. All right, so now that you have a free chlorine in the atmosphere, it's going to interact with an ozone molecule, right, which is an O3. And that chlorine is very reactive, and what it's going to do is break the bond of the ozone molecule, literally breaking up the ozone. All right, so now you have a chlorine-oxygen bond. And that chlorine-oxygen bond is chlorine monoxide. And that doesn't last too long. All right, because that chlorine monoxide is susceptible to bumping into another O2 molecule. All right, and when it does, let's say our chlorine oxygen bond, plus an O. When the chlorine monoxide bumps into a free oxygen, you're going to again free up that chlorine molecule. And that's the big problem. Alright, one chlorine molecule through this process, one chlorine molecule can destroy thousands and thousands and thousands of ozone molecules. Hundreds of thousands of ozone. Alright, so natural UV radiation will free up that chlorine from the CFC, and then that chlorine will go ahead and break the bond of an ozone molecule, literally destroying ozone. Alright, leading to the formation of chlorine monoxide, which doesn't last that long in the atmosphere. Alright, all it has to do is combine with an O molecule, a free oxygen. Alright, and then that oxygen bond will reform and free up the chlorine again. That's a real big problem here with CFCs, is that when a chlorine molecule is up there, a free chlorine, it can destroy hundreds of thousands of ozone molecules. Alright, we saw that ozone will form naturally, but the rate at which ozone is destroyed is greater than ozone formation. Okay, so literally a hole in the ozone layer from the use of these CFCs in the 1950s, 60s, and 70s. I've seen this question on the AP test. Alright, you're going to want to know this formula, this process. And if you have questions, come in and ask. I'll be free to help you. Okay, and here's another little diagram to show you the same process. So if I sounded confusing to you, go ahead and check this out, take a look at it, and try and understand this process and this chemical formula. Okay, if you need this slide, stay put here and listen for a few moments. If you know your electromagnetic spectrum, you can move on. But just to recap, the electromagnetic spectrum, alright, this is all light in the universe. Okay, this is our reality. And visible light is just a portion of our reality. It's just a portion of the electromagnetic spectrum. And I'll go through real quick, and it has everything to do with wavelength. And I'll go from shortest to longest wavelength. The shortest of the wavelengths, okay, we call gamma. And gamma radiation is very, very dangerous. Okay, we use that in industry. It's found in stellar death, supernova. A gamma burst nearby in the universe would greatly impact life on Earth. Luckily, cosmic gamma rays are blocked by our atmosphere. Thank you, atmosphere. Okay, the next shortest wavelengths are X-rays. Okay, and you know that they're useful in medical application. All right, X-ray, those are also blocked by our atmosphere. So I'll do this. So you have gamma rays at the shortest wavelength. X-rays have a very short wavelength. A little bit longer, but still high energy radiation is your UV. Alright, and it goes UVC is the strongest, UVB is the next strongest, and then UVA still can impact your skin, common cause of wrinkles later in life. Alright, and then comes visible light. Alright, now we're into the spectrum that does not really harm you. Alright, and then after that is a little bit longer of a wavelength. We're going to call this infrared. Whoops. Infrared energy. Alright, that's outside of the visible spectrum, associated with heat energy. Alright, snakes and other creatures have infrared sensors. You're giving off infrared energy right now in your hands, in your armpits. Alright, if you could see it, it would be outside the visible spectrum, outside the red portion, so it would be red. Okay, infrared is commonly used in restaurants to heat food. So that's infrared energy. Okay, it's still a longer wavelength. We have our microwaves. Alright, microwaves, you know what those are used for. They're used to cook food. And just an FYI, inside the box of the microwave, energy, microwaves, are sent through your microwave, your appliance. Alright, and those microwaves, that energy hits the water inside of your food. So if you picture a piece of pizza in your microwave, the microwave radiation will hit the water in the food, instantly boiling that water, transferring its energy into the water molecule. That water molecule will heat up and transfer its heat to the food and then evaporate in the process. So if you've ever had something put in the microwave and you get it out and it's very dry, All the water molecules have been boiled, transferring their heat to your food, and your food has been warmed, and the water is now gone. So your food is warm, but dry. So you have to get the timing right. You want some of those water molecules left so that your food is tasty and not dried out. Okay, so microwave energy. All right, now the last on the spectrum, the longest wavelengths here are radio waves. All right, useful in transmitting information. Very interesting that we can put information on a radio wave and send it out into the atmosphere, and a receiver can capture it, decode the information, and you can listen to music or the radio or a talk show. All right, very interesting that this portion of the electromagnetic spectrum, you can put information on it and send it out. All right, so that's the electromagnetic spectrum. That should be a review. Okay, our sun emits energy from the infrared into the X-ray. Okay, gamma ray is blocked by the sun or by our atmosphere. X-ray is blocked by our atmosphere. UV is somewhat blocked. Visible gets through. Okay, infrared is blocked. All right, microwaves are blocked. Radio gets through. Okay, so I teach in astronomy, if you want to see things in the universe from these types of objects, you need to have a space telescope. You have to go above the atmosphere because the atmosphere will block all those. So we have space telescopes that look at objects in space only in the microwave, only in the infrared, X-ray, gamma ray, and so forth. All right, very beautiful objects out there, but you cannot see those things from the surface of the Earth because they're blocked. All right, so there's a quick little refresher about the electromagnetic spectrum and how it applies here. Okay, and you can take a look at this and just get a little bit more of a graphic image about what we're talking about with UV and the spectrum and how it is absorbed in our atmosphere. Okay, so what were we doing that really created these CFCs? Where are the sources of ozone depleting substances? Refrigeration. Okay, if you look, refrigeration, servicing, and manufacturing accounts for over 50% of the production of CFCs. All right, halons are about 11%, and foams. Halons are fire extinguishers. Okay, some pesticides have halons. All right, and then there's aerosols at 22%. So we were using CFCs very commonly in spray cans and as a propellant. Okay, so those are the sources of ozone depleting substances. And just think about the future and, you know, current warming trend. There's going to be an increased demand in refrigerants and coolants. So, you know, we need these chemicals. We found alternatives, but you can see the demand for refrigerants and coolants. Okay. All right, here's a little cartoon. You can take a moment. All right. I like this cartoon. All right, to give you a date there, 1982. There used to be the mentality that it's okay, you know, there's no proof that CFCs are causing damage in the ozone layer. You know, it was a common misconception. People just didn't know. The data wasn't out there. The studies weren't done yet. All right, it was just coming out at that point in the early 1980s. It was discovered that it was really damaging our ozone layer. And I like this cartoon because, you know, 1982, long time ago, before you were born, the child knows about CFCs, probably learned it in his AP Enviro class. But, you know, what are we doing today that we're running around saying there's no proof, there's no danger, oh, don't worry about it? You know, we continue to use pesticides and herbicides, insecticides in our homes. All right, we're using BFRs, brominated flame retardants, in our pillows and mattresses and carpets. And, you know, we'll talk about it in class that we're just absorbing chemicals into our bodies and exposed to things that someday we'll look back and say, you know, we shouldn't have done that. And now we're running around saying there's no proof, there's no danger. It's just part of society. So I like this cartoon for a number of reasons. And then in the 1980s, we discovered the ozone hole. Okay, and it was formed over Antarctica. A lot of people say, why? Why Antarctica? Well, at Antarctica, due to a rotating body, all right, there's these polar stratigraphic winds in the stratosphere, these winds, and they cause a temperature decrease, which is perfect for ozone depleting chemicals and a thinning of the ozone layer. And when you have a thinning of a layer and the destruction of a layer, it's even going to be thinner, and in fact you can get a hole. All right, and that's what we were seeing. We measured a hole in the ozone layer. All right, and it has to do with these polar stratospheric winds. Okay, and here's what the hole looked like. All right, it took years and years. Now you're going to see in a couple slides that we started banning the use and manufacture of CFCs in 1987. Okay, but it takes time for those molecules to get into the stratosphere, focus and concentrate into the polar region, and then destroy ozone. So even after we banned ozone, the hole was still growing. Okay, it takes time. We're only now seeing a rebuilding of the ozone layer. Okay, and here's a couple more dates. 1987 is our magic number for when we banned the use of CFCs, and you're going to see little details on that. But we started measuring that growth in the ozone layer, and you see it goes from blue in October 1980, a small blue circle, grows till look at 1985 when you see purple now. All right, 1987, the hole was about the size of North America at its largest. All right, and we measured a reduction in the ozone layer around the poles of around 50%. Okay, very dangerous stuff. So at the bottom there it talks about the ozone layer and how it's measured. All right, you want to associate ozone and the units of measurement as being Dobson units. All right, and if you think of a column of air, if you walk outside, there's a column of air above your head all the way to the top of the atmosphere. All right, the number of molecules, the actual number of ozone molecules in that column of air is called Dobson units. Okay, so the average at any given place would be 300 Dobson units. So 300 molecules of ozone are above your head. So if you squeeze them and made them a layer, you're talking about 2 to 3 millimeters in thickness. Okay, so not that much ozone, but very important that it's up there. Okay. All right, here's some effects of ozone depletion. All right, skin cancer and cataracts. All right, and that's a human physiological impact. All right, along with mutations. All right, it can also impact plants. Increased UV radiation to the earth would reduce crop production. All right, would reduce algae in oceans, so less producers would mess the food chain up. It could also lead to climate change. More energy reaching the surface would warm things up, all right, causing additional global warming. All right, so there's a lot of effects here, and let's take a look at some of the human physiological effects. A cataract is common in elderly population, the youth of developing nations. All right, your dog or your pets might have had a cataract, and exposure to UV radiation will cause a clouding in the lens of the eye. All right, and that clouding could lead to blurred image. A cataract nowadays is a common procedure. Okay, you just make an incision at the pupil of the eye, pull out the cloudy lens, and insert a clean new lens. All right, but like I said, exposure to UV radiation over the course of one's life leaves one susceptible to cataracts later in life. Okay. Maybe one of your grandparents, my grandparents, used to wear the glasses in the top right there to reduce UV radiation. Okay, and then that brings us to issues with the skin and the layers of the skin. Okay, so take a look at this image here. I have UVA and UVB. Now, I mentioned that UVA radiation is relatively harmless. It penetrates through the epidermis and into the dermis, the lower levels of the skin, which turns out to be pretty healthy. All right, that causes the production of vitamin D, all right, which is good for bone health. It's good for immune health, and it makes you feel good. It gives you a tan. All right, a tan is evidence that you got a healthy amount of vitamin D, a healthy amount of UVA radiation. All right, but UVB, stronger radiation. All right, a shorter wavelength. UVB does not penetrate the skin. In fact, it'll burn the cells of the top layer of the epidermis. All right, here's the epidermis, and here's the lower level, the dermis. All right, now here, this burning is is basically cell destruction. And what's interesting is your cells, a sunburn are your cells committing suicide. Your cells would rather commit suicide than be damaged or mutated. All right, if we didn't get a sunburn, we would get skin cancer at every sunburn. All right, there would be mutation every time. A sunburn is evidence that your skin, the cells, committed suicide instead of succumbing to mutations. All right, because skin cancer is mutations. All right, and if those mutations, that cell mutation, gets into the bloodstream, now you have what's called full-blown melanoma. It's known as skin cancer. Okay, so what we need to do is be aware of our moles, areas of sensitive skin. All right, it's because we need to monitor them for any sign of mutation. All right, if I go back real quick here, here's a picture of a 35-year-old melanoma survivor, and if you look at her skin under ultraviolet light, you can see that her skin really has a lot of freckles, okay, that are unseen in the visible wavelength. So her skin is sensitive. Okay, some of our skin is sensitive, and those are the areas that we want to be careful with. Okay, to prevent the spread of any mutated cells, we would have to cut away that area, not only the mutated cells, but some of the healthy skin and cells around it. Dig it out and make sure that it doesn't spread into the bloodstream. All right, so keep an eye on yourself for any irregularity in any moles, and just make sure you visit your dermatologist regularly. And we need to take care of ourselves. Okay, so regarding the ozone hole, all right, we're expecting a near full recovery by 2050, so let's have a party and celebrate the ozone layer for its protection of life on Earth, but also for the fact of that it will rebuild itself, even though we tried our best to knock it out. And that's a little bit about the ozone hole and the ozone layer. So what are we doing to prevent ozone depletion? And this will wrap up this discussion on ozone. There's been law passed. All right, in 1987, the Montreal Protocol was designed to have countries come and acknowledge CFCs as an ozone-depleting chemical. Okay, and in the lower left there, they decided to reduce the production and use of CFCs and other ozone-depleting chemicals to 50% by 2000. All right, 24 countries signed that original Montreal Protocol, which took place in Montreal, 1987. If you notice, they re-met 3 years later in 1990 in London. Okay, there was new research that came out. I showed you some of those images of the ozone hole growing and growing, and it really accelerated the need for more countries to get involved. So 93 countries in 1990 met in London to sign into the Montreal Protocol, all right, and reduce the use and manufacture of CFCs and other ozone-depleting chemicals to 50% by 2000. 2 years after that, in Copenhagen, what's known as the Agreement in Copenhagen, it amended the original Montreal Protocol and called for a complete 100% ban by 1995. So if you're gathering this, they really realized through new research and data that this is a serious problem, and instead of 50% by 2000, we need to really just completely ban the use of these chemicals by 1995, which gave them 3 years to do so, if you can imagine that. All right, 140 countries have today signed the Montreal Protocol, and it goes down in history as one of the most successful laws to be passed or to be signed by countries to reduce the production of an ozone-depleting chemical. All right, if you take a look here, you can see in the late 1980s, when these laws were passed, the Montreal Protocol took effect. Immediately, the production of these banned substances went down until fairly recently it was next to zero. Okay, hasn't been completely banned by all countries. However, this has been a tremendous success in litigation. Okay, a lot of people say, what are we doing now? We've replaced CFCs with HCFCs. We attach a hydrogen on there, and it is not completely clear of destroying ozone, but it has much less an effect. And you can think of it as the rate of replenishment almost equals the rate of destruction. All right, it still destroys, but not nearly as much. Okay, so it's a safer chemical. All right, or we're replacing CFCs completely with other coolants. All right, and then the third thing there to reduce ozone depletion, we need to collect and reuse all existing CVCs. All right, we don't want to manufacture and produce any more, and that's required under the new Clean Air Act. Okay, which we're going to talk a lot about. That Clean Air Act is a huge piece of law. Okay, so I'll end here with this little cartoon, and I hope you gained more of an appreciation for our ozone layer, and you learned and understand how it not only forms but was being depleted by human actions. Okay, and hopefully you also see the need to reverse those human actions. You know, when we learn that something has a negative impact on the environment, we do have the power to turn it around. We do have the power to say no and choose healthy and clean alternatives. All right, and this is proof. So ozone teaches us that we humans can and do have an impact on large-scale systems, Earth systems. And it also is proof that we can change if we all put our minds to it and act together. Thank you, and I'll see you back here for a discussion on more variable gases.